section is on correlation, and we talk a little bit about cause and effect. This section is a little bit different because instead of having one set of data, we have two. And the idea is to see if we can find a relationship between the two different sets of data. Now, we do have a couple of vocabulary words here. When we have two variables together, you have to think back to like algebra class. Our two variables are going to be x and y. And when we put them together, x and y, we can graph those, and each xy pair would make a point. The x variable is the one that comes first. It's called the explanatory x and x explanatory variable. And in the next unit, we're going to be talking about x and y variables again, only the x will be called the independent. It's really just, I don't know. There's not a real reason why we have two different words for it. It's just the context that we're using it in. Y, on the other hand, is the response variable, also known as the dependent variable. So I didn't want to just spring the vocabulary on you in the next unit. This time we'll talk about explanatory and response. Next time it's independent and dependent, but it's all just x and y. Now, what happens when we have a bunch of dots that we graph and we don't connect them? We call that a scatter plot. This is the example of a scatter plot. Now, this looks like a mess. If you're expecting something like from algebra class where you look at a graph and your job is to connect the dots, well, that's the wrong idea. In this case, we're not looking for a pattern that we can connect the dots with. We're thinking more like, what if I have a great big fat marker? A great big fat one. Is there a way that I could make a line, because I am talking about lines, is there a way for me to make a big fat line that would hit all or most of those dots? Well, okay, so I'm sitting on a couch, so I made a little bit curve. But yeah, a big fat line could hit all or most of those dots. That means we have a correlation. We have a relationship. Now, if we go back to what we learned in algebra class, if we make a line that goes up from left to right, that would have a positive slope. So a correlation that goes up from left to right is a positive correlation. We want to know, again, could we take our fat marker and can we draw a line that would hit all or most of the dots? Again, I'm sitting on a couch, so I made a bump. But yeah, in this case, the line goes down from left to right. I forgot to change my thickness. Down from left to right means a negative slope, which means in this case we have a relationship that's a negative correlation. If you have a set of data that basically looks like it's just raining, and there's not really a slanted line that you can make that goes up from left to right or down from left to right, your only options are really to go straight across or straight up and down. That means there's no relationship between your x and y, whatever that may be. And there's one more thing that can happen. I can see a pattern in the dots, but the pattern isn't a line. This pattern makes more like a L. That's an exponential relationship. So what that means is there's a relationship, but it's not a straight line. So we don't call that no correlation. We call it a nonlinear correlation. Linear means lines. We're looking for a linear correlation. If it's nonlinear, it means it's not a straight line. So if we put some of these concepts together in a graph, we have a graph, and the first thing we're supposed to do is identify what's the explanatory variable, what's the response variable. Explanatory variable is on the x-axis. The x-axis is identified as hours of training. So hours of training is the explanatory variable. The response variable, that's the y-axis. The y-axis is identified as the number of accidents. Now, the blank space there is for you to describe the relationship. If I look at this relationship, it goes down from left to right. The pattern of dots goes down. So that is a negative correlation. But we also want to think about whether it's weak or strong. A weak relationship has the dots more spread out, so they're more loosely connected. A strong relationship, the dots are pretty close together. In this case, they're pretty close together, so I would call this a strong negative correlation. Now, when you talk about how the graph is read, you always start with however the x-axis is. As the x-axis increases, well, on the x-axis are the hours of training. So the first part of this sentence says, as the hours of training increase. Now, the x-axis will always increase because when we read a graph from left to right. Look at the x-axis as we go from left to right. On the x-axis, we go from 0 to 5, 10, 15, 20. If you go from left to right on the graph, the x-axis is always increasing. So as the hours of training increase, now we want to talk about the y-axis. Number of accidents. What happens to the number of accidents as we go from left to right? So there's where we're kind of following our line. If we move along our line from left to right, our line is going down from left to right, so the number of accidents decrease. And that's what we would expect. If we have training, we would expect the accidents to decrease. Try the same thing with this graph. Maybe pause it. X variable is the SAT score. The response variable is the GPA. Oops, that's a P in there. This graph goes up from left to right, and the dots are pretty close together. So this is a strong and positive correlation. As the SAT score increases, the GPA goes up, so it increases. Now, if we take a look at this graph, again, the explanatory and the response variable, you can always answer those. So x-axis is labeled height. The response variable is labeled the IQ. And when I look at the pattern of the graph, it doesn't appear like I can make a line that slants upward or one that slants downward to actually hit the dots. This is a case where the only real line I could draw is straight across. If the only line you can draw is straight across, that means there's just no correlation. Oops. Now, there are a number of reasons that we can say two variables are correlated. One of them is sheer coincidence. The other is a common underlying cause. And last, we can call something a direct cause. Now, if you want to say it's a direct cause, you literally have to say X causes Y to happen. You want to be wary of calling something a coincidence too quickly, because sometimes a common underlying cause It takes a little bit of thinking to figure it out. So let's look at some examples. First, we're going to read the correlation and decide whether the correlation is positive or negative. No arguing with whether it's true or not, just is it a positive or negative relationship. At the beach, when more ice cream is sold, more people drown. More ice cream, more people drown. That's an increase and an increase. So as X increases, Y increases. That's a positive correlation. It's also a true correlation. So let's go through our possible relationships. Unlike what Grandma might tell you, eating the ice cream is not what causes people to drown. So it's not a direct cause, even if you're eating the ice cream in the water. It's also not a coincidence. Like I said, it's easy to jump to that when two things seem pretty unrelated. But put a little bit of thought into it. When do you think they sell more ice cream at the beach? What's going on when people are buying lots of ice cream? It's summertime. It's warm. It's a nice day. It's a hot day. If they're selling a lot of ice cream at the beach, it's probably because there's a lot of people there on a nice hot day. If you have a lot of people at the beach on a nice hot day, you've probably got a lot of people getting in the ocean. The more people at the beach, the more people are going to get in the water, the more people are going to drown. So our explanation for the correlation is a common underlying cause, which could be something as simple as a summer day. Automobile gas mileage decreases with tire pressure. This one's kind of tricky. If I want to say my automobile gas mileage decreases, depends on which axis I put it on. Let's say my gas mileage is on the Y. If my gas mileage decreases, that means it's going down. Now, what does it mean decreases with tire pressure? Decreases with tire pressure means the tire pressure is also going down. On the x-axis, that means we're going left. Well, how do I draw a line that goes left and down? That's actually a positive correlation. Now, I'm not an automobile mechanic, but in my limited knowledge, I would call that a direct cause. How about this? In a large resort city, the crime rate increased as the number of taxi cabs increased. Again, we have an increase and an increase. Two increases make a positive correlation. Now, unless you think that taxi cabs or the taxi cab drivers are committing the crimes, it's not a direct cause. It's also not a coincidence. To support more taxi cabs in a city, the population needs to increase. If you have more people, the crime rate is also going to increase. So this is a common underlying cause. And the common underlying cause would just be more people. In Angela's class, the taller students get lower grades. Taller implies an increase, lower implies a decrease. If you have two positives, if you have two increases, that's two positives. Two positives make a positive. If you have two decreases, two negatives and two negatives also make a positive. The only time you get a negative correlation is when you have one increasing variable and one decreasing. That makes a negative correlation. Now, if the taller students are getting lower grades, hopefully that's just a coincidence. I mean, unless you've got something against basketball players. Now, there's a separate video showing you how to use the calculator to make the correlation and the scatter plot on the calculator. So please refer to it to finish the rest of your notes on this section.